Intel City, a platform where you can learn, teach, research, and repeat.
This is Nexys 4 FPGA board. Nexys 4 is powered by Artix-7 FPGA device. On this board we have a lot of 7 segment displays. We have total 8 digits and 16 switches. In this example we will explain you how to interface these switches with this 7 segment display for various projects. You can see this output 1, 3, 2 and so on. So let's start the video.
So let's start working with the 7-segment display interfacing on FPGA using Nexys 4 FPGA kit. The contents of these videos are this video is actually divided into 4 parts. First, we are gonna give you overview of the 7 segments. What are 7 segments and how they work? What are their types and how you can use them in the FPGA board in any given FPGA board. And then we are gonna see the working of the Verilog code. The Verilog code in the Verilog code we will design a hex to 7 segment conversion code. So it will be basically a decoder which will convert the hexadecimal format to the 7 segment format, and I'll explain you that code to you. And then finally we will explain you complete implementation on Vivado design software, and that will involve how to make a project on the Vivado software, and then how to simulate the Verilog code, and then we're going to give you the pin layouts, and then we are going to implement that design or our FPGA kit. So let's start with it. So first of all, the block diagram. This is the block diagram of the Hexer 7 segment display. So there are basically 2 types of 7 segment displays. One is called as common cathode, and the other one is called common anode. So what we have right now in our FPGA device, the common anode type. Basically the 7 segment display or 7 segment digit is consists of basically 7 LEDs: 1, 2, 3, 4, 5, 6 and 7. So these 7 LEDs, and of course LED is a light emitting diode, and diode has a positive part, or you can say the anode part and the cathode part. So to switch on this LED, we have to derive this terminal, the anode terminal, to a high voltage, and this terminal to a low voltage, or you can say this from at this terminal should be connected to the ground or zero, and this terminal, the anode terminal, should be connected to the positive terminal, VCC, or you may call it logic high or 1. Okay, so we just simplify the same things that uh, from anode side you have to provide it 1, and from cathode side you have to provide it 0. So common anode configuration is just like this, that the anodes of all LEDs are combined together to form a single terminal, or you can say a pin, and that pin is called common anode. Okay, and all other pins, or you can say the cathode terminals of these diodes, are placed over here. And for example, to switch on this LED, for example B LED, I have to provide input of this. For example, this is if B input, so I have to connect this to the 0 or ground, and I have to connect this anode to 1. 1 means a logic high, or positive side of the battery. So this way the B LED or LED, this segment will glow. So similarly I can all of the segments, and make different patterns. For example 0, for example 1 and 2 and 3, 4 and so on. So in FPGA board, in the Nexys 4 FPGA board, I have basically 8 7 segment displays which are connected like this. And here are the common anodes: the AN0, AN1, AN2, AN3, AN4, AN5, 6 and AN7. And these are the data lines. You may call it data lines, or you may call it the cathode terminals. So this is DP as well. DP is for decimal point, because we have a point over here as well. Okay, so basically the data will be coming from this side, and the data will go to that anode, that 7 segment digit which is enable. Okay, so this common anode is acting as an enable. So whichever the 7 segment or digit is enabled, the data will go to that one. If we enable them all, then the data will go to all of them, because these data lines are common. And if we enable only one, only two, or any specific 7 segment, then the data will go to that specific 7 segment. Okay, so in our case, we are going to design a decoder which will be connected to the input of that decoder will be connected to switches of the FPGA board. So we have 4-bit input. So this is 4-bit input, and the output is called A to G, and it is 7-bit output. It goes from 0 to 6 to 0, or 0 to 6, and it is 7-bit output. So 7 bits will be connected to these 7 segments, the A, B, C, D, E, F, and G points. Okay, here is how it can be done. This is our truth table. This is, for example, the input coming from switches. There are 4 switches, so we can write it over here, like 0 can be represented in binary like 0000. 1 can be represented as 0001, and similarly 5 can be represented as 010. 7 can be represented as this, 0111, and similarly we can represent 9 as 1001, and F can be represented as 1111. So this is how the input will be coming from the switches, and that input will be translated or decoded into the language which this 7 segment understands. So this language is this one. So I'll just explain this to you. A, B, C, D, E, and F. So these are the A, B, C, D, E, F, and G. A, B, C, D, E, F, and G. These are the LEDs which are marked over here. So to switch on this one, like is for 0, we have to pass. Of course, as I told earlier, that we have common anode type 7 segments. So common anode type of to switch on 7 segment, which is having common anode type 7 segment. So to switch on, we have to connect these terminals, these LEDs to 0, like A, B, C, D, E, F, and F. These will be on. Here you can see these LEDs are on, and 1 will be off. So G is 1, so 1 will, G is, this one is G, this one is G. So G is, you can see here, off. So here 0 represents 0 is, you know represented as this digit, like these configuration of LEDs or setting of LEDs shows 0, and here it shows 1. In case of 1, we have to switch on only B and C, so B and C should be connected to 0. So let's see, B and C is here 0, and all other inputs, or you can say the LEDs, are connected to 1. So similarly for 5, for 7, for example, for 7, where is 7? This is 7. So for 7, A, B, and C are on, and other all LEDs are off. So A, B, and 7. Okay. Uh, Okay, so A, B, and C are on, and all other are off. So similarly, for 8 we have for 8 is very unique number in a way that all LEDs have to switch on to show the number 8. So here we can see all LEDs are on. So all LEDs are connected to 0. Okay. So this is how it's done. This is a truth table of this LED. Now let's move on to the FPGA. So this is the circuit layout of the Nexys 4 FPGA board, and similarly, it's very much similar to the Nexus 2, Nexus 3, and this is FPGA board. And you can find this on the website of the manufacturer. Or okay, you can find this information in the manual product manual of the FPGA board. So here you can see that these are the switches. This is FPGA board, FPGA module, or these are the switches, switch number 0, SW0, SW1, SW2, and SW3. So we will use these four switches which are connected to U9, U8, R7, and R6 inputs. Okay, so we'll use these switches for input. And here is the 7 segment display. So we have eight 7 segment digits, and in this case, in our this example, we will only use this one. And okay. So this one is, these are the data lines, A, B, C, D, E, F, G, and decimal point. So these data lines are connected to L3, L1, L5, L4, K3, M2, L6, and M4. So this information will be required because we have to connect our this module output to these pins, and similarly we have to connect these pins are working as input, so we will connect those pins of the switches to this input of our module, of our Verilog module. So this was about the data line like A, B, C, D, E, F, G, and decimal point. And about this, about enable, or you can say common anode. Common anode is enabled through a PNP transistor. You can see over here we have PNP transistor. So PNP transistor is activated by providing 0 on the base. So from here we have to provide 0, and 0 will activate this PNP transistor, and the current will flow down here, and this common anode will get high voltage. So this way we have to provide 0 from the FPGA. From FPGA we'll provide 0 to the enable point like N6, M6, and then uh, it will be inverted by the PNP transistor, and actual 7 segment will get high voltage on the anode side. Okay, so let's go to the Verilog code. Here's our Verilog code of the decoding operation of the decoder. Here we can see this is our top module. A top module we have input. Input is switch SW, which is represented by SW, and it is a 4-bit signal. So the output, we declare this as a wire, and it is a 7-bit signal which is called A to G. So this is 7-bit output, and this 7-bit output is actually the data which is going to the 7 segment. Okay, the next output is the enable, that is the common anode enable based operation. So we have 8 digits, as I have mentioned that we have 8 digits. So we have a 8-bit signal which is AN. Okay, and in this example we will disable all 7 digits, and we will just enable one of the digits, or one of the first 7 segment digit. Okay, so we have 8-bit enable signal, and we will use it whatever whichever 7 segment digit you want to enable. You just have to make it 0, and it will be enabled. So here we have another 1-bit signal, that is DP, decimal point. So decimal point is also connected to all of the 7 segments. So here in the code, in the main code, we assign the AN to 8-bit output, that is all are 1. 1 means disable, and 0 means enable. As I told in the previous slide, that it is connected through a PNP transistor. So PNP transistor is activated by providing 0 on the base. So we have to enable any digit, we have to provide it 0. Okay, so we are enabling the first digit over here, and then we are disabling all of the bits. And the decimal point dp is 1. And here in the third line, we are calling, or you can say, we can instantiate another function of another module which is available over here. And that function is hex to 7 segment D1, and it is the input coming from the switch as W is passed to the X over here, and then the output to from this module which is going to 7 segment is connected to A to G. Okay, so these are connected together. X is connected to the switch, and this A to G is connected to A to G of this module, which is finally connected to the 7 segment. And in this module, we have input wire X, which is connected to switch, and then this is the output. And always block, we have a case statement. We are using case statement where if the input is X is 0, like from the switches, if we get 0 0 0 0, then the output will be this. So this is the same output which we saw in the truth table. Okay, and this is, for example, A, this is B, C, D, E, F, and G. Okay, so in this case only G is off. G will be off. All other LEDs will be on. So in this case you can see that A, B, C, D, E, F, C, D, EF, these are all on, and only this F is, which is in the center, is off. So it represents 0. So for example, similarly, if we have for example, if we have 7 on the input side, the user if provides us a 0 1 1 1 or from the switches. So this 7 is decoded to this number which says that 0 0 0. Okay, so let's decode this one. So it says that A is on, B is on, and then C is on. For example, this is A, B, and C. So you can see this is A, this is B, and this is C. All other LEDs will be off. So this is how the number 7 is represented in the 7 segment. So similarly, this decoding operation is performed using this case statement, and then this is AND case and module, and this is all for our for this is all we have in the Verilog coding. Now we go to Vivado software, and we just learn how to make a new project, and then how we can uh, synthesize this code, and how we can connect it to the pins on the FPGA board, and how we can implement this on the FPGA board, which is Nexus 4 in my case. Okay, so I just opened the Vivado software. I have downloaded this the product manual of this Nexus 4 FPGA board. This is called reference manual. It is available on the Digiland website. So it's very useful, and I just show you some parts from this reference manual. Just opening the 7 segment part. This is the 7 segment part which I just discussed with you, and these are the switches which we are gonna interface, and then these switch 0, switch 1, switch 2, and switch 3, and these are 7 segments, or 7 segment digits. 8 digits are available with us, and we just want to show the output on only one digit in this example. So this is Vivado software, and I just make a new project new. In from this window, I'll click next, and this is the name of the project, and this location of the project. So in my case, I just select it just like this, project 1, and it's going to this directory. Just click next. This is RTL project. Yes, this is RTL project. And here, if you have already Verilog files, then you can add these files here as well. I don't have files, so I will create new files. Next, click next, and from here I have on FPGA, my FPGA board, I have this Artix-7 FPGA, which is XC7800T. So I will select my device XC7A100T CSG324. So this is my device. I just select my device and then click next and then click finish. So this software will make a project for me, and for that, in that project I have to add some files. Okay, on the left side you can see this is Flow Navigator. Here we have Project Manager, IP Integrator, Simulation, RTL Analysis, Synthesis, and Implementation uh, steps, and then finally we have Program and Debug step. Here's the summary of the project, and here from in this window I can see sources. Okay, sources are the files which I have in my current design. So currently I don't see any file because I don't have any file in these sources. So I will just click on this add sources from this project manager. Add sources, add or create design source. Okay, and then I create file. Name of the file will be, for example, this is top module, so I just top module. This is name of my file. I just click OK, finish. Okay, yes. Okay, so this file has appeared in the design sources here. I double click it to open it, and you can um, expand it. So I just remove these commands, and then I just remove this, and I just copied the code which I explained to you earlier. So I just copy that code. Okay, and I will just now go to, I've copied this code and I just go to this RTL analysis block because I have to run the RTL analysis. I click the OK. After this step, I will be enabled. It will enable me to connect the output of my module to the pins. To the input side will be connected to the switches on the FPGA board, and the output side will be connected to the enables and the 7 segments. So here is my overview of the RTL analysis. Here the FPGA software has converted my code into a block, and in that block we have input which is called SW from 3 to 0, and the output is called A to G. Okay, so this is my main block, and then I will just click on this and I click IO planning. This is very important. From here you can see down on the bottom side you have package pins, IO ports. So IO ports, I will click this tab, IO ports tab, and here you can see all of the ports in your design. So in from this I will just expand it, and I will, because we are using 3.3 volt system. Let me just show you. Okay, here let me just go it. Okay, here it says 3.3 volt. Okay, so all buttons, all switches, all LEDs are operating on 3.3 volt. So I will select, from here I will select LVCMOS 33, and for this also 33 means 3.3 volt. So this is also, so I have selected LVCMOS 33. Okay, here is the scalar port which is DP. Here also I select this one. Okay, let me just connect these switches to the input side. For example, this switch 0 is connected to U9, switch 1 will be connected to U8, and similarly switch 2 will connect it to R7, and then switch 3 to R6. So I just do it on this side. I'll click on this package pin. So SW is connected to U9, U8, R7. These are pins of FPGA, and R6. So switches are connected. These switches are already, the directions is set as in. In means input. So DP is connected to, for example, I connect the DP to M4. Let me just check it out. So DP is connected to M4. Okay, so this is connected to M4, and other points like for example A is connected to L3, N1 is connected to B, and C is connected to L5, D is connected to L4, and so on. So I have noted these pins, and I just combine them together in this design. So 8G and G6 is connected to L3, and 5 is connected to N1, 4 is connected to L5 pin of FPGA, and 3 is connected to L4 pin of FPGA, and then 2 is connected to K3, M2, and L6. So these data lines are also connected. Now we go to enable. So we have 7 segment displays or digits. So you just connect them to the 7 segments. Okay, so AN0 is connected to N6, N1 is connected to M6, and then it's connected to M3, and 5, and 2, and 4, L1, and M1. So this is also done. AN is also connected, A to G is also connected, and we have connected the scalar ports to the pins as well. Okay, just we click Control S just to save this, and a file will be created, my XDC file. I just named this file as my XDC file. This file is a constraint file. Constraint file is having information about the constraints or the design constraints, like for example, which output is connected to the which pin of the FPGA. So these are constraints. So I just go to project manager, and then I go to this constraints, and I just click this one just to see this file. So this is the file which is automatically created based on my choices of the input output layout. So whatever I have done in the graphical user interface, using an interactive interface, and that is converted to this code. So we can directly use this. We can directly make this XDC file as well. So I will use this XDC file, and just I will click on run synthesis, number of jobs, I give it maximum processing power to save the time, and now it is synthesizing my circuit. Synthesis means that circuit is connected to its netlist, and its layout will be generated, and it's actually the circuit will be constructed from the Verilog language. The software will make a circuit of the decoding operation, and then in the next stage we will do implementation. In the implementation phase, the software basically implements, or you can say implement the circuit created by the synthesis step, using resources of that FPGA. Okay, so for example, in my FPGA I have lookup tables, and I have multiplexer. So that is the implementation step. So I just click run implementation from this. I can also click from here run implementation. So it's implementing my circuit to the resources available in the FPGA kit, like multiplexers, like lookup tables, and things like this. Implementation is complete and is successful. If you have not configured these pins in a correct manner, if the voltages are not good enough, if the circuit is not connected correctly, the pin selection is not appropriate, then the implementation step will cause an error, and you can just go back and check uh, the layout, the pin layout of your design. Now I click on this generate bitstream. I can also click on this generate bitstream from this flow navigator. So this generate bitstream will create a bit file for me which can be downloaded to the FPGA board, and that is basically the design which is loaded on the FPGA. Now the bit stream generation is completed, is successfully completed. There is no error, and I just open the hardware manager to program this code to the FPGA. I just cancel it and I just open the click on this open hardware manager. You can allow it or cancel it, whatever your choice. And I just click on this open target auto connect. My FPGA device is connected through USB port, and this Vivado software has identified the FPGA device which is connected through USB. I'll just show it to you. So this is my device which the software has detected, which is connected, and I just click on this device and just click on this program device. So this is um, by default this bit stream, the .bit file, top module .bit file, this is the bit file which is created as a result of my core, my all project. So this file will be selected as a default. So if you want to change it, then you can change it from here as well. So I just want to load this default file to my FPGA board, so I just click on this program. Now it's programming FPGA board. It says programmed FPGA board, and now I can check the output on my FPGA kit. So let's go to FPGA board to check the output.
Now we have implemented our design on this board, on this Nexys 4 board, and now we are ready to test the input. We have interfaced these four switches with our decoder, which is used to decode the binary or the hexadecimal input to the language which 7 segment understands. Like you can say, it is decoded into the language of the 7 segment digit. So this is the first 7 segment digit which we have used in this example, and these four switches were used in our case. So we will just provide input to our circuit now. Now the input is 0, all zeros, 0 0 0 0. So the 0 is displayed here. Now I just press this first button, which is 1, so it's 1. I provided 2 like this, and then 3, and then 4, 5, 6, 7, 8, and 9, and so on. So this was about this example. This is how you can use this 7 segment in your projects.